The calculations for a confidence interval for one population mean. The calculations for a confidence interval for a population mean are used to estimate, with a given degree of confidence, a range or interval that is believed to capture a population mean called mu. The estimate is based on a sample of size n from the population that has been found to have a sample mean x bar. The estimate depends on the level of confidence desired for the interval, which is commonly 90%, 95%, or 99%, but can be any large percentage. The calculations depend on whether or not the population standard deviation sigma is known or assumed known. If it is, we use the formula x bar plus or minus z times sigma over the square root of n, where z is the z-score for which the desired amount of probability, that is, the level of confidence, is in between this z-score and its negative on a standard normal distribution. For example, suppose we want a confidence interval for the population mean amount of money a customer spends in a single transaction. We have a sample of size n equals 50 customers and have found the sample mean is x bar equal to $43. Also suppose that we know or are told to assume that the population standard deviation of the amount spent is sigma equals $13.75. Because we know sigma, we find the z-score on the standard normal, for which the desired probability is between the z-score and its negative. This can be done using a normal table or a normal distribution calculator. For example, if we wanted a 90% level of confidence, we find that a z-score of 1.645 is appropriate, since 90% of the probability on a standard normal is between negative 1.645 and positive 1.645. In this case, the confidence interval for the population mean mu would be x bar plus or minus z times sigma over the square root of n, which equals 43 plus or minus 1.645 times 13.75 divided by the square root of 50, which equals 43 plus or minus 3.20, which equals a range of 39.8 to 46.2. Thus, we are 90% confident that the population mean amount spent per transaction is between about $39.80 and $46.20. Note, if we switch to another confidence level, the z-score changes. For example, for a 95% confidence interval, we would use a z-score of 1.96. For a 99% confidence interval, we use a z-score of 2.575. For any other level of confidence, we use a normal table or calculator to find the appropriate z-score. For instance, if we wanted an 80% confidence level, we would find the z-score needed is 1.282 because 80% of the probability is between negative 1.282 and positive 1.282 on a standard normal. However, it is often the case that the population standard deviation is not known or assumed, so we must use the sample standard deviation S, which we estimate from the data. Then, instead of using z-scores from the standard normal, we use a t-distribution with n-1 degrees of freedom to find the value t for which the desired amount of probability, that is the level of confidence, is in between this t-value and its negative. Thus, if sigma is not known, the formula we use is x bar plus or minus t times S over the square root of n. For example, again, suppose we want a confidence interval for the population mean amount of money a customer spends in a transaction. Suppose we have a sample of size n equal 28 customers and have found the sample mean is x bar equal to $40. Because we don't know and haven't been told the value of the population standard deviation sigma, we instead calculate the sample standard deviation from the observed sample data. Suppose we found this value as to equal $14.50. Because we don't know the value of sigma, we find the t-value on a t-distribution with n-1, in this case 27 degrees of freedom, for which the desired probability is between this t-value and its negative. This can be done using a t-table or a t-distribution calculator. For example, if we wanted a 99% level of confidence, we find that a t-value of 2.771 is appropriate, since 99% of the probability on a t-distribution with 27 degrees of freedom is between negative 2.771 and positive 2.771. In this case, the confidence interval for the population mean mu would be x bar plus or minus t times S over the square root of n, which equals 40 plus or minus 2.771 times 14.50 divided by the square root of 28, which equals 40 plus or minus 7.59, which gives us an interval of 32.41 to 47.59. Thus, we are 99% confident that the population mean amount spent per transaction is between about $32.41 and $47.59. Note that the t depends on both the level of confidence and the sample size n, since it is always based on a t with n-1 degrees of freedom. For example, for a 95% confidence interval in a sample size of 20, a t-table or calculator for n-1, which is 19 degrees of freedom, shows that the t-value needed is 2.093. For a 90% confidence interval in a sample size of 15, the t-value on a t with n-1, which in this case is 14 degrees of freedom, that gives 90% of the probability between t and its negative, is the value t equals 1.761. Lastly, for an 86% confidence interval in a sample size of 9, we find a t-value of 1.638 is such that 86% of the probability is between negative 1.638 and positive 1.638 on a t distribution with n-1, which in this case is 8 degrees of freedom.